So here's a video going over every problem that I posted in the PDF from yesterday. So it's still just the same PDF. I'm just going to explain each step just in case you guys had questions on it. And if you still have questions after watching this video, feel free to email me. All right, so looking at number 1 where we have to find numbers. This is a lot like the first example off of the in-class examples we did on Monday. We're given the fact that the sum of two non-negative numbers is 20. We want to find the numbers if A, the sum of their squares is as large as possible, and then part B of this, or the second part of this, as small as possible. And then for part B, one number plus the square root of the other is as large as possible, and then as small as possible. So for part A, just as we set up for the in-class example, we're going to let x be the first number and then 20 minus x be the second number. And since these are two non-negative numbers whose sum is 20, we're staying between 0 and 20. So just to point out, anytime we see this, we have a continuous function on a closed interval, the extreme value theorem applies. So you don't necessarily have to show the number line for the first derivative and then do the sign chart for it. You could just make a table of values. Anytime you have a continuous function on a closed interval, we could just make a table of values. So setting up the function for A, it says the sum of their squares. So that's what we're looking at here. We're going to have x squared plus the quantity of 20 minus x squared. So it's a little bit easier than the function we set up for the in-class example. And then I just expanded this. So expanding the 20 minus x gives us 400 minus 40x plus x squared. Combining our x squared terms, we get this. Over to the right here, I find the first derivative. We ask ourselves two questions about that. Where's our first derivative? 0, so we just set 4x minus 40 equal to 0. We get x equals 10. It's never undefined. And then here we set up our table, including the 0 and the 20. We substitute it back in, so these are our outputs. Now, because we're using the extreme value theorem, you want to say it. So we want to say, by the extreme value theorem, the max sum is 400 when the numbers are 0. And then 20, because the second number is 20 minus the 0. And then the minimum sum would be 200 when the numbers are 10 and 10. So for part B, it's very similar here. Now this is more like the one we did in class. One number plus just the square root, we had the cube root, one number plus the square root of the other is as large as possible, as small as possible. So again, as we learned from our in-class example, let's put that second number first and use that as one number, and then the square root of the other would just be square root of x. This is what we get off to the right here if we find the first derivative. Ask ourselves these two questions. Again, the fact that we're between 0 and 20, we know that this first derivative is undefined when x is equal to 0, which is the first endpoint. And then we set this equal to 0, and we only want the positive, so x is equal to 1/4. We create a table. 0, 1/4, and 20 are what we're using here. So we say by the extreme value theorem, the max sum turns out to be 20.25 when the numbers are 1/4 and 19.75, because that's just 20 minus 1/4. And then the minimum sum is 2 radical 5, or you could use a decimal equivalence, when the numbers are 20 and 0. Okay, let's take a look at number 2. Here we have to maximize area. What is the largest possible area for a right triangle whose hypotenuse is 5 centimeters long? So we want to start by just making a picture of this, and we call the two sides, the two legs, x and y. The hypotenuse has to be 5. So from this, our function just comes from using the Pythagorean theorem. X squared plus y squared equals 25. Let's just solve it for y. And remember, we have to have positive values here, so y would just be the square root of 25 minus x squared. That way we get everything in terms of x. So area of a triangle is 1/2 the base times the height. So y would be the base, and x would be the height, but y is now in terms of x, so we have 1/2 times the square root of 25 minus x squared times x, and I just rewrote this here. Now if you take a look under the square root here, or even over here, we know that x has to be between -5 and 5, but even more so, we know we have to be between 0 and 5. But if we just write it this way, we're still on a closed interval. So carefully going through here, using the product rule, here's our u, and then all of this right here is v prime, and then here's our v u prime. Carefully taking this first part, turning it into a fraction. The 2's cross out. Well, 1, 2 here. We still have another 2 that drops down to our denominator. And then we're just left with a negative x squared up top. And then we have this 2 times the square root of 25 minus x squared. Over here, we just have radical 25 minus x squared over 2. So to get common denominators, I just have to multiply the second fraction by radical 25 minus x squared, top and bottom. So now I'm just left with negative x squared. These two just turn into a 25 minus x squared all over the LCD. Combining our like terms, this is what we get. Asking ourselves the two questions: where is our first derivative equal to 0? Or where is it undefined? So again, as I pointed out, the domain is really 0 to 5. Even though having an answer of 0 isn't going to help, because we're trying to maximize area. So if we set 25 minus 2x squared equal to 0, we end up getting 5 over radical 2, or you could rationalize this. Again, we only want the positive length. And where is it undefined? That would be when x is equal to 5, but that's the other endpoint. So evaluating our area function at these three values, this is the result. So we could see we're going to get a max area here. So again, we say by the extreme value theorem, the max area is 6.25 square centimeters when the hypotenuse is 5 centimeters and each leg measures 5 radical 2 over 2 centimeters. So even though I got x to equal to 5 radical 2 over 2, I just substituted it back in just to make sure, or to see what y is. And it actually turned out to be the same as well, 5 over radical 2 or 5 radical 2 over 2. All right, for question 3, we are maximizing perimeter. We're asked, what is the smallest perimeter possible for a rectangle whose area is 16 square inches, and what are the dimensions? So we're trying to maximize perimeter, but we start with, we're given area. So if we just draw a rectangle, and we know the area is 16 square inches, and area is equal to base times height, or we could call it x times y. And we know that that's 16 is equal to x times y. And if we called x the length, this would be y, which would be the width. So y would be 16 over x. So that's where we're coming up with this from. And then we set up a perimeter function, which would be 2x plus 2y. And y is just the 16 over x. So then just distributing that, we get 2x plus 32 over x. And then here's our derivative. We would just get 2. And I imagine this is 32 times x to the negative first. We end up with minus 32 over x squared. Ask ourselves two questions. Now for this, I'm not worried about a domain. So we could just use our number line here. We don't have to use the extreme value theorem. So when I set the perimeter, the derivative of the perimeter function equal to 0, we get x squared is equal to 16 as we solve it, but again, we only want a positive value. Undefined when x would equal 0, but x can't equal 0 because we need to have a width to have a rectangle. So my only critical number, I can't go below 0. I'm going to have 4 as my critical number. So I want to test this. I just want to substitute it back into the first derivative, which is right up here. So imagine this is a 1. We would definitely get, sorry, this one up here. So imagine if x is a 1, we would definitely get a negative value. And if x is greater than 4, let's say it's 5, we would get a positive value. Because imagine that would be 2 minus 32 over 25, so that would be 2 minus a 1 point something, which would be positive. So underneath this, this indicates that our perimeter function is decreasing until we get to 4, then increasing. Therefore, we have a relative min at x equals 4. And I know at the very beginning it said maximizing perimeter, but if you go back to the problem, it said what is the smallest perimeter? So we really want to minimize the perimeter. So this is justifying that we have a relative min at x equals 4. So we could have done this, or what I was teaching you guys about the second derivative test for extrema, we could have found our second derivative, which just turns into 64 over x cubed, evaluated at x equals 4, see that it's positive, so we know that we would be concave up around x equals 4, therefore we'd have a relative min at x equals 4. So you don't have to do both, just one or the other will suffice. And then we would just evaluate what is our perimeter function when x equals 4, and we get 16. So the minimum perimeter happens to also be 16, but 16 inches when the dimensions measure 4 by 4. And all we have to do is go back and substitute it in up here. When x is 4, we would get a y would equal 4 for 16 over 4 up here as well. All right, looking at number 6, the largest rectangle. This is very similar to example 2 that we did in class and finished yesterday. So we could just make a quick sketch of our parabola here for y equals 12 minus x. Again, our rectangle has its base on the x-axis, so our base would be 2x, and our height would just be y, which is 12 minus x squared. Right up here is our area function, base times height. We just distribute that. We find our first derivative. Now, I didn't use the extreme value theorem in example 2, and you don't have to either, but you can. We know we just have to go from 0 to 2 radical 3 for our x value, so we could use the extreme value theorem. So we can make a table of values. But regardless, we're still going to answer these two questions. So our first derivative is equal to 0 when x is equal to positive 2 only, not a negative, and it's never undefined. So now, because I have a closed interval, we're just going to go from 0 to the 2 radical 3. And I got the 2 radical 3s here simply by setting 12 minus x squared equal to 0. I just found the x-intercepts of our parabola here. And evaluating each one, we get 32 is going to be the max. So we'd say by the extreme value theorem, the max area is 32 square inches when the dimensions are 4 by 8. So if x is 2, our base is 4, and then we'll get 12 minus 2 squared, which will give us the 8 inches. All right, looking at number 9, the best fencing plan. A rectangular plot of farmland will be bounded on one side by a river and on the other 3 sides by a single strand electrical fence. So we can draw a little picture here. So here are the 3 sides of fencing. We want to maximize the area. With 800 meters of wire at your disposal, what is the largest area you can enclose and what are its dimensions? So I'm going to call the 2 equal sides x, and then the remaining third side would just be the difference between 800 and these 2x values, so 800 minus 2x. So area is just base times height, so we just do side times side here, distribute. Our first derivative then is 800 minus 4x. Here's where our first derivative is 0, again never undefined. Now this one, I found it to be a little bit easier if we found our second derivative. Again, you could do the first derivative number line, it does not matter. But our second derivative just turns out to be a negative 4. Notice there's no variable here, so that means it's always concave down or concave down everywhere. So even if I evaluated it at x equals 200, I'm still going to get a negative 4, which is still less than 0. So we're still concave down. Therefore, we have a relative max at x equals 200. I find the area when x is 200, and that's 80,000. So the max area is 80,000 square meters when the dimensions are 400 meters by 200 meters. And all I have to do is go back up to our picture. This would be 200. This would give us 400. All right, now this last example, I want to take our time going over it for 32 part A. And this talks about strength of a beam. The strength S of a rectangular wooden beam is proportional to its width times the square of its depth. So I'm going to talk about that over here on the right. S is proportional to its width times the square of its depth. So when we set up what we call like a direct variation problem, we take a constant here and we always put it in here. That's what it means to be proportional. You multiply it by a certain scale factor. So S is the strength of the beam, is proportional means we're going to take K and then times of its width times the square of its depth. So W is the width, square of D is the square of its depth, and then times K. So K is going to be a constant. Then they give us this picture here. We want to maximize the strength of the beam. So because it actually creates a right triangle in this cross section here, I'm going to just say d squared plus w squared equals 144. Just use a Pythagorean theorem. But we're trying to maximize this function here. So I want to solve it for d. It'll just work out a little bit easier here because we have to square d. We'll get rid of that square root. So if I substitute that in, s is going to equal k times w. Now I have everything in terms of w. And notice when I go to square the square root, it's going to cancel. So now I just have s is equal to k times w times 144 minus w squared. Recall k is a constant. So I just want to distribute this here. Now I'll find the first derivative of s. So we're going to find s prime. So remember, k is a constant, so the derivative of this first term is just going to be 144k minus, and then we get minus 3k w squared. So I want to know where that's going to equal 0. It'll never be undefined. So if I set this equal to 0, remember, k is a constant, so I could just leave this constant over here, add 3k w squared. I could divide both sides by 3k, so the k's cancel. I'm left with 48 equals w squared. Taking the square root and simplifying, I get just positive 4 radical 3 only. And again, I'm going to do the second derivative test for extrema. I'm going to find the second derivative of the strength of our beam. That just turns into be a negative 6kw. Because remember that 144k is just a constant, so that turns into 0. Evaluate that at 4 radical 3, which will always be negative then because the 6 is negative. So that will be less than 0. So we're concave down around this x value. Therefore, we have a relative max at w equals 4 radical 3. And we just want to find d. So using w is equal to 4 radical 3, this is the calculation we get, simplifying the radical. So we would say, therefore, the strongest beam has dimensions of 4 radical 3 inches by 4 radical 6 inches.